Swayam Prabha. Digital India. Educated India.
Hello, Namaste. I'm back with the next set of module wherein we would start with looking at how do we do a querying, how do we look at georeferencing. Georeferencing is to tell you that which portion of the Earth's surface that particular picture belongs to, which means that I'm trying to tie the coordinates, tie the map to certain part of the Earth's surface, which means as soon as you click on the map, it has to say where actually it belongs to through using certain reference system. So today we will look at how do we do georeferencing, what kind of different systems are there, and this entire week would be we would be looking at different projections, how what is a geoid, what kind of geoid are there, and how we look at a geoid as a reference point. Then what are the datums, how do we look at datums, and then we would also look at certain coordinate systems, and probably at the maybe the end of this week or the next week we would also we'll start looking at how to use the software, any GIS based software. For example, we would take up with QGIS first. So in today's class we would look at querying first, then we would go into georeferencing system, different georeferencing systems that we have, like the continuous georeferencing system and the discrete georeferencing system. Now when I in the previous class I did maybe in the first set of lectures or in the second set of lectures I did define GIS as a data store, a toolbox and a technology, and science behind the technology that is actually driving the entire set of information to be stored, retrieved at any point of time. So this is what I informed it. I defined GIS as defined by many. GIS is a telescope, microscope, and also you can say that it is a storage of information in certain set of databases, so that it can be retrieved at will, analyzed at will, and also produce outputs at will using certain data manipulation techniques or data inference techniques. So GIS always consists of an input or a georeferenced image. Okay, so when we are looking at any data, this has to have certain reference to the Earth surface. So that's how we call it as a georeference. Geo means earth referenced image. So then you should have a storage, then you look at the analysis, that you do a query or analysis or you do statistical techniques, then you have a display and output of the spatial data. So that depends on how do you want to present the output data in whatever presentable form that you need. So when we look at querying, maintenance and spatial analysis is the most distinguishing part of the any GIS. So that's how it is different from any of the static functions that you may find in any other kind of systems. GIS is, that's why it's the most distinguishing part. It contains all the three systems in it. It starts with querying, it starts with maintenance, it also ends with a spatial analysis and output of data. But no other systems which is comparable to GIS has all the three parts together. So when you look at GIS, its functions for spatial analysis, operators that we use for spatial analysis data to retrieve new geo informations. When I say new geo information, these are the informations that we can get from clubbing one or two sets of data, one or two sets of information that is already stored in the database. Using those data sets, we derive a new information. That's what I define here as a new geo information, new geo outputs. Special queries and process models play a very important role in meeting the user needs. Whenever you are looking at it, all the models that we looked at, using those models, those type of data models, we try to do the spatial query, and these query yields whatever the results that is necessary for information that on the real world in the form of a data model. When we look at the combination of a database, a GIS software, the rule and the reasoning mechanism, this leads to something called as a spatial decision support system. Now, when, for example, let me tell you, let me give an example. Now, let's say government wants to build a new township. How does it understand what are the real factors that is influencing that particular region, and how the outgrowth may be after 15, 20, 30, 40 years. So how do you look at it basically? So the first thing that you would look at is how the city has grown over a period of time, and how it may grow if that township has come into that effect. So if you have to look at it, you will look at what are the different plans that government has in around the township. Maybe if it is closer to the city, along the roads that lead to that township, or along the lanes that lead to the township. Then if there are certain other plans that have come up, or if there are industries that are already there, if there are certain other basic requirements that are already there. So you have to look at all of these aspects. Once you look at this, then you can easily understand, visualize how a decision can be taken. So now you know spatially what is there at what place. Now using those spatial features, you try to decide how a particular township has to be located, where it has to be located, what may be the maximum capacity or the maximum population of that township. Okay, such kind of analysis can be done, and what may be next 20 years, 30 years down the lane, if this township grows at this particular rate as the city has grown over a period of time, what may be the population or the outgrowth at that particular stage. It may have outgrowth, or it may have a confinement to that region, but what is the kind of growth that it may have, and what are, very importantly, is that if these are the growth poles, for example industries, if there are certain industries, if there are some hospitals, if there is some other economic, socio-economic activities based agents in that particular region, what are the how are these agents actually playing an important role in developing that, it will play an important role in next 10-15 years in developing that entire township. So all of these decisions can be taken spatially, visualized, and then the plan can be made. Doing such thing would actually help in providing all the basic amenities that most of our cities lacks. So what we do normally is that we build the entire urban system, then look at what is the necessity, keep on adding the necessity, and finally when the threshold is reached, we will not be able to satisfy any necessity of that particular city, because the city starts expanding, start growing, and making it a confined place, or making it looking at certain amenities to the citizens may be extremely difficult. That's what majority of our cities are facing today. So if you understand the concept how the decisions can be taken spatially, then it would be easy for us to develop that particular part of urban system. So now I gave you an example of urban system. This can be applied into huge number of applications, whether it is forest management, whether it is water management, or whether it is any of the other aspects. This spatial decision support system can provide an important input in terms for planning. The next thing that we would look at is querying, maintenance, and spatial analysis. So when I say certain things, for example, in a general way, if I say what is, so it is actually when we are displaying a map, report, or a table, we are trying to define what may be its name, or what may be the address of a particular maybe a particular building or a particular place in that particular map. That is what we are trying to query in English form. But in a GIS function, we are trying to look at the storage and querying that particular function. Okay, where that particular data has been stored and what is the quality of that data. So, we are trying to do that. But when we look at other query like what pattern, now in a normal English we are looking at, when I say pattern in that particular data, whether all parcels in the area size is greater than 2000. Okay. So, but in a GIS function, the query functions with constraints. It means to say there are certain constraints for the particular query that is, and you are making a query. For example, the constraint here is greater than 2000. Anything that is greater than 2000 is queryable. Okay. So, if let us say in a general way, what if, so now we are trying say that what would be the situation if this is the pattern. Okay. So, that is nothing but a modeling function. We are trying to see if there is a scenario change in this particular pattern and what would be the result of that particular change. So, that is what is how the querying is done. So, why I have given you this example is to make you understand in a real English the way you speak and how the querying happens. So, it has to be translated from the real kind of language to the queryable form in GIS functions. So, this is just an example for you guys to understand how it has to be done. Now, when we have a GIS querying, three classes are most important for querying and analysis, that is maintenance, the maintenance and analysis of the spatial data. So, when I say spatial data, these are the data that is actually is associated with the geo information of the earth surface, right. So, then maintenance analysis of the attribute data, the data that is related to the spatial data, which is of information and which is of the thing that you need for your analysis, is stored as a attribute data. So, it has to be maintained and analyzed. Okay. Then integrated analysis of both spatial and attribute data. So, that is extremely important when you are actually looking at the entire database. So, we can do various operations when I say this. So, you have attribute data, you have maintained the attribute data, you have a spatial data, then using both you can do several operations on your database through the spatial analysis. So, for example, you have a search operation wherein it can be a thematic search, it can be a spatial search, etc. You have a location analysis for when you are looking at a buffer, a corridor, etc. You have terrain analysis when you are looking at a slope or aspect. You say, oh, if the slope is greater than so and so, so this has to be threshold. So, that kind of analysis can be done. If the slope is greater than this, so threshold this region, only this region can be used for certain kind of maybe developments. So, then distribution or neighborhood functions like cost, diffusion, spread, the proximity. For example, you say there let us say that there is a particular industry. In the proximity of that industry, next 5 kilometers, maybe it may not be feasible or it is not good to have human habitations there. So, such kind of, so if it has to be marked spatially as the non-habitable regions, so you will have to draw it spatially and say such kind of proximity analysis can be made. The nearest neighbor analysis can be made, which is if there are huge number of parcels around and you want to find out for a particular parcel which is the nearest neighbor, such analysis can be made much easily by just a small query. So, then is the measurements query, wherein you can do the measurements of a certain region. If you have a polygon, you can even measure the area. If you have a line, length of that particular line, etc. So, these queries are defined based on attribute, based on the spatial queries, and deriving new data from already existing data that you may have. So, such kind of analysis also can be made. Now, once we have understood what is a query, so we will do certain queries when we are looking at the database functions in a software. We will first what we will do is that we will take up a system, we will show you how you georeference a particular file, then how do you add attributes to a particular file, then if you want to do certain analysis inside the attribute table, how do you do it, then how do you retrieve that information, how do you show it as uh, a thematic data, how do you query a thematic data. So all of these things we'll learn when we look at our practice sessions, maybe in the 10th and 11th week. So till then we'll understand all the concepts of GIS. Then once we have understood everything, then probably we can look at how the software goes. But next week we would look at an introduction to the QGIS, so you would understand how the software works. So you can download it and install it so that the practice sessions can start parallelly. So next we look at georeferencing systems. When I speak about georeferencing system, whenever you look at any geographical data, okay, it requires a referencing system to for a common system of maintenance or uniformity. Okay, for example, let us say I develop a map, I develop a georeferenced map, and someone else develops a georeferenced map, and there is someone else, the third person, who is again developing a georeferenced map. Now all the three of these maps, if it has to be compared, it has to be in the same referencing system. Okay, otherwise one map sits somewhere on somewhere else on the earth's surface, whereas the other map may sit somewhere else. So comparative analysis of all these three maps would not be possible. If it has to be possible, it has to be in the same georeference style. So now that it is to say that when you are converting a 3D map into 2D, a 3D earth surface into 2D earth surface, you will follow a certain way of georeferencing style. So this referencing style is actually pinpointing that particular area on the earth surface using certain ways and methods of referencing. When you start pinpointing, you are saying that this is the way I am looking at the earth surface. So that is why you need a georeferencing system. Next, georeferencing is defined as positioning objects in a 2 or a 3D space. So I gave an example of 3D earth, putting it in a 2D, but you can always look at georeferencing system as the one wherein you are positioning your objects. It may be in a 2D space or in a 3D space. There are two types of georeferencing system, and when we look at very principal methods, it is continuous georeferencing system, that is also called as relative and direct. We have different types, I will speak about this. Then we have discrete georeferencing system. So we look at the continuous georeferencing system and discrete georeferencing system in our next set of slides. So when we look at georeferencing, as I said, we have two types. One is the continuous georeferencing, other one is the discrete georeferencing. And when we look at continuous georeferencing, it is divided into two types. One is relative, other one is direct. Okay, so when we look at relative, it is based on polar coordinates. Okay, when I say polar coordinates is a continuous system in a 2D coordinate system. Each point on a plane is determined by the distance from a reference point and the angle from the reference direction. So which means to say that you have a reference point, okay, from which you are trying to find out the distance to a reference point, okay, and then you are also trying to have an angle from a reference directions or a reference line or a reference region. So using this, you do a polar coordinates. If you look at your Cartesian coordinate system, you use the reference system in order to look at what the angular or the point position at a particular plane. So that is nothing but your planar coordinates. Now when you look at the other way of looking at it is a direct referencing, that is using an elevation referencing. You can look at the datums. I will speak about the datums in the next class. Then the coordinate systems, which is extremely important. This is where people actually have don't understand the difference between a coordinate system, a projection, a datum, etc., which is extremely important when you are looking at any GIS system. Okay, if you look at discrete, it can be just like your address, your postal code, your grids, your zones. So all of these are an example of a discrete system. Okay, and when there is a discrete system, it is actually referring to a certain point on the earth surface defined globally. Okay, so if I say my pin code is 721302, there is no other pin code which is actually 721302 on the earth's surface defined. Okay, so that is how it is very discrete in terms of representations. So discrete is basically your the representation that you have given in the form of address, pin codes, etc. When you look at continuous, you have two types, relative and direct. And when you look at direct, we have elevation referencing, datums, coordinates, and map projections. So all of these things has to be looked at. So you have to be extremely careful when you are handling all of these systems. Okay, so first let us understand certain very important aspects. So when we normally look at earth, okay, the way we are taught is earth is a sphere, right? So but when you look at earth's surface, earth is basically not a sphere, it's a spheroid. Okay, so when I say spheroid, if you look at here, the sphere is a complete round shape, whereas the spheroid here, you do not have a round shape, but it is bulged at the center, flat at the bottom. Okay, it is bulged at the center and flat at the bottom. So that's called a spheroid. Okay, spheroid has a major axis and a minor axis. That is what is represented here. Okay, if you want to represent a spheroid, so if an ellipsoid or a spheroid is obtained, when, please be very specific here, ellipse is rotated around an axis. You have an axis that is passing through the center of the earth's surface, you rotate an ellipse across the rotational axis, you get the output as a spheroid. So your earth is basically a spheroid and not a sphere. Okay, so now once we have understood earth is a spheroid, so we look at what are different georeferencing systems. The first thing is continuous referencing. So continuous referencing implies continuous measurement of the position of a phenomena in relationship to the reference point with no abrupt change or a break. Okay, so when I say continuous, there is continuous value that is referred without any break, and also the phenomena is in relation to the reference point. So always we have a reference that we use in a continuous system. And when we look at continuous system, it includes direct georeferencing, which involves coordinates on the curved surface of the earth, or it's called as coordinate system. Okay, then geocentric coordinates or datums. Datums are extremely important. Then rectangular coordinates, or it's called as map projections. Please remember the coordinate system, datums, map projections, and also as the vertical coordinate or elevations or elevation referencing. So we will discuss all of these in the next session. Okay, so when we look at continuous georeferencing system, so coordinates on the earth surface of x comma y. So it can be a lat long system where represent these positions. For example, if I am looking at this point, is represented by the x and the y coordinates. Okay, when you have a 2D representation. So normally if you have looked at a lat long system, it can be in degree decimals, it can be in degrees, minutes, seconds. So any of those formats that normally you use is belongs to the lat long system. It's dependent on the user what kind of system he uses. So then also it is known as a geographic coordinate system or a GCS. Okay, then you have geocentric coordinates, which represents the position as an x, y and z coordinates. This is in a 3D. So it's called a geocentric. The point 0 comma 0 is defined as, if you see this, okay, is the center of the earth. Okay, this particular point that is being referred here is the center of the earth. It is 0 comma 0 comma 0. As you move here, all your points are mentioned in terms of x comma y and z. Okay, that is relatively referenced from the center. Then you have rectangular coordinates. So this is, for example, let us say is an UTM, Universal Transverse Mercator system, which represents the position as xy coordinates. Okay, but its units is in meters. It's extremely easy for us if it is in meters, because it will help us in easily calculating the distances, etc. So, the one of the systems is called as UTM coordinate system. This is also known as a projected coordinate system. So, now we have understood what is a coordinate system, what is a datum, what is a projected coordinate system, right. So, now let us get into direct georeferencing. So, direct georeferencing is defined, as I said, the first thing that it always looks at is the earth is not a perfect sphere. Okay. So, it goes into saying that earth is not a perfect sphere. It is expressed in as a shape of an ellipsoid, okay, ellipsoid or a spheroid. Now, the components of a georeferencing map, please be extremely sure about this. You have datum, you have map projections, and you have coordinate systems. So, looking at all of these three things are extremely important when you are looking at any of the maps. Okay, what coordinate system this particular map is, what is the projection of a map, and what is the datum of a map. So, if you understand these three things, then you will be able to successfully read a map and look at a map details in much better way. Datum is an ellipsoidal model. I am repeating the previous slide. Datum is an ellipsoid model of the earth used for geodetic calculations. Okay, map projection is a projected curve surface of the earth into a 2D. For example, if this is the earth surface, the circular earth surface, it's a 3D data. Now, if you put a light here in front of this earth surface and project it, keep a paper here. So, now you are projecting a circular earth onto a paper. So, you are projecting it on paper. So, now it becomes a 2D, because you have only the reflections, you cannot look at the third dimension of the earth surface. So, you are projecting it on a 2D. So, this kind of projecting system is necessary for us to convert a 3D data into a 2D data for us to understand the details on the earth surface. Then you have coordinate system. It is a reference grid system. It helps in geometrical computation of the earth surface. Otherwise, you will not be able to compute exactly the geometrical region where you are located, the x, y, z components. Okay. So, keep all these three things in mind. The first thing, as soon as you look at any of the digital map, is if it is georeference, please look at its coordinate system, its its projection system, and then datum. Because most of the students, even today, whatever I see is that first, as soon as they get map, they will be enthusiastically looking for what data I can gather. But the first thing you have to look at where it is. If it is not in a proper coordinate system or a projection that you basically need, so please project it into that particular system, then use that map for any kind of analysis. Okay. So, this is about the direct georeferencing. Now, let us look at the next part of slide, wherein we have three types of transformations, such as cylindrical transformation, conical transformation, and then azimuthal transformations. So, these are the transformation which convert the earth's surface from a 3D to a 2D. So, this is to represent a curved surface of the earth into a planar surface of the map, as I explained previously. Now, when I look at a cylindrical surface, so if let us say I consider this as an earth surface, whatever this particular thing is there. So, if this is the earth surface that I am considering, now I roll a paper across this, something like this. Okay. Now, print whatever is represented on the earth surface and open the paper. That becomes your cylindrical projection. You are opening a paper like a cylindrical boundary. So, now whatever is printed from the earth surface to this cylindrical boundary that is what is projected from your 3D surface to on a 2D paper map. That is nothing but you called as cylindrical projection. And when you look at a conical projection, you have your earth surface like this, then now put a cone like this. Normally you know about your ice cream cones, right? So, when you put a cone on this, okay, now your the conical shape, the sharp shape is here, and the bottom is the most widest part. Now now I have a light that is beaming like this. I open up the entire space. Okay, whatever is that is printed here on from the 3D earth surface on a 2D earth surface is a representation from a 3D to a 2D. This means to say that your data is now projected in a form of a conical projections. Okay, I'll discuss each of these in details. I'll also say what is the advantage and what is the disadvantage in my next coming lectures. Then the third one is called the azimuth projection. Now you have your earth surface like this. Okay, I keep either a paper like this or like this or like this. Okay, the way you want, if it is near the poles, slanted, or below near the south pole. Now once you have done, add a light opposite to where the paper has been kept. Whatever the projections that you see is nothing but the projection on from that point on the earth surface. For example, if this is your earth surface and you have kept a paper like this, put a light across like this. So now with this light, the entire earth is projected on the paper. That is nothing but your azimuthal projection. Okay, so you have three types of projections. You looked at cylindrical, conical, and azimuthal projections. We will look at certain things, certain more details about all of these projections. What are the advantages of direct georeferencing? Is it covers entire Earth's surface. It can be transformed to any coordinate system. Okay, but yes, it is accompanied by a disadvantage. The elevation referencing system is not the same for a normal national elevation system. So I'll speak about this again in my next class. So you'll be able to better understand what it means. To summarize this particular lecture, we looked at querying. As I said, querying is about maintenance and spatial analysis. You can do a huge lot of spatial analysis just like your English language, but the querying defines it in its own way of how the data is to be analyzed. Then you have georeferencing system. There are two types. One is continuous, one is discrete. Continuous, you have a continuous value where the data is referenced. Discrete has its own representation, for example like a postal code or an address. Then we defined a shape of a earth. A shape of earth is nothing but a spheroid, and it's not a sphere as we would think all the time. Then we have two types of georeferencing. The continuous georeferencing we looked at. Then discrete georeferencing, we looked at the projections, the cylindrical, the conical, and azimuthal projections. In the next class, we would discuss more about georeferencing system. For example, what do you mean by an elevation referencing, which I spoke as a disadvantage in my previous slide. Then the relative referencing and the discrete georeferencing. So when you compare all of these, you would be able to understand what kind of referencing system you should look at and why elevation referencing system is extremely important. Okay, with this I would end this particular lecture. Thank you very much. Have a nice day.